So let me end by giving you a quick overview of what will be in this course, and which is more or less the same, what will be in the textbook that we're using. So the textbook that we're using is called Introduction to Experimental Mathematics, and I wrote it together with Rune Johansen, who used to be a postdoc here in Copenhagen and who has been developing this course together with me over quite some time, something like 8 years, I guess. When we started trying to teach experimental mathematics, we of course tried to see if we can find a textbook, and somewhat to our surprise, it didn't seem possible to find such a book. We made notes, and these notes eventually became this book. The book isn't quite finished yet, so the status is that it's supposed to appear around New Year. We're almost done with the proofreading and so on. We're just discussing some aesthetic issues with people in charge of organizing the text to make it look nice and so on. But it's finished enough that we can use it in this course, and I have asked and gotten permission from Cambridge University Press, who are publishing this book, to give you a free copy. They just insisted that I give you that copy on paper rather than electronically, so that's why I've printed out the first 3 chapters, and I'm hoping that when we reach the time when we're going to need chapter 4 and so on, that actually I will have the final version and not the one that says proof here. But essentially, the table of contents of this book will be more or less the same as the weekly program of this course. So essentially, these are the 8 chapters in the book. The introduction chapter, I've tried to cover some of the most important features today. Then there's Maple that we will look at on Wednesday, and then iteration and recursion is the program for next week. So actually, maybe I'll just switch to this page, which tells you what are the contents of the 7 weeks of this course. So the first week, the one that we're in now, introduction and basic programming. Second week is iteration and recursion, which has to do with writing programs in Maple. And let me point out that we are not expecting that you know how to program Maple or anything else to begin with, but we're going to teach you the basics of that. Then visualization, symbolic inversion, pseudo-randomness, time memory and precision, and linear algebra and graph theory. These are the chapters. And let me just quickly give you an idea what will be in these chapters. So the theme of week 1, 2, and 6 is the very fundamental theme of writing algorithms. And of course, this is essential when we're doing experiments on a computer. We have to tell the computer what the computer needs to do, and we do that by specifying an algorithm or a program in Maple. But of course, there's many ways of doing this, and there's many pitfalls and problems, and this will essentially be the theme for the first 2 weeks to get you going on writing programs in Maple, knowing the basic options you have when you design a program, and also getting an idea of an efficient way of actually writing programs and making sure they do the right thing. And then we revisit this issue in in week 6, which is chapter 7, which has to do with the problems that you will usually encounter when you write algorithms that maybe they run too slow for you to get the amount of information out that you were hoping for. Maybe they need all the memory of your computer. Maybe they're not precise enough, and so on. And these are issues quite close, actually, not to mathematics, but more computer science, that we will have to look at when working seriously with experimental math. but we're postponing the more complicated issues to the 6th week. So let me just give you a quick idea of how we're going to work with algorithms, because you may not be familiar with this idea. We're going to work with pseudocode, and pseudocode is a way of specifying an algorithm or a program in a way which is sort of halfway between what a computer might like and what a human being might like. So we've specified here the way that the Sieve of Eratosthenes works. So this is a very classical way of computing a list of primes, and you can see that it's something which is a mixture of keywords like while, end while, return, which is somehow something that you would expect to be something that a computer would like to read, and then some general words, human sentences like construct a list, remove IP from L, and so on. And this this sort of hybrid between human readable programs and machine readable programs is actually a very good way of working with designing programs. So what we would like you to do when you need to write your own algorithms is to do it in some sort of stepwise refinement process, where you first make a very coarse description of what you expect the algorithm to do, using perhaps a few of these keywords, and then this will be something which is very close to the human being. Then you will maybe think more about how to do these things. For instance, like in line 5, remove IP from L for each integer I bigger than 2. This is something that you then would need to specify further for the computer to understand it. But the existence of having these pseudocodes will turn out to be very useful. First of all, it's a very good tool for writing programs, but it's also a very good way of communicating programs. So instead of giving you the technical code that explains how the Sieve of Eratosthenes works, this is actually a much more efficient way. So let me just give you an idea of how this works. So I'm just using Excel here to visualize what I mean. So you can see I've done step 2, and I've constructed a list of numbers from 2 to 23. So here n is 23, and then I let p equals 2, and I'm going to go through this while loop. So it's something that's going to be repeated as long as p is strictly less than, in this case, 23. So what I'm going to do when I reach line 5 is that I'm supposed to remove IP from L for each integer I bigger than 2. So what I need to do is I will take, remember p is 2, and I will take the numbers of the form I times 2, so that's all the even numbers, but only where I is bigger than or equal to 2. So what line 5 is explaining that I should do is that I should remove the entries 2 times 2, 3 times 2, and so on until they're all gone. Right? So I'm keeping the 2 is a prime, but I'm removing all the multiples. Oops, wrong. All the multiples of 2. So in a sense, I'm just removing all the even numbers. Right? So this is what the Sieve of Eratosthenes tells me to do. And now I've reached line 7 of my program, and then now I'm reaching line 6 of my program, and what I'm being told to do is now let p be the smallest element in L that is greater than the previous p. Right? So see if I can find my my Excel again and see if I can get back to this. So p is now 3, and then I loop back again, and I'm supposed to remove all the multiples of 3. So there's first 6, which I've already removed, and then there's 9, it's gone now, and then there's 12, I removed that already, 15 is gone, there's 18 and 21 is gone, and so on. And now I'm reaching 5 in the while, and I'm supposed to remove all the multiples of 5. So actually there aren't any left, because there's 10 and 15 and 20, we already removed those. Then I'm going, p will be 7, and I'm supposed to remove all the powers of, the multiples of 7. There is 14 and 21, they're gone already. And then there's 11, there's 22, it's gone already. 13, 26, it's gone already. 17, there's actually no multiples left in my little list here. And so when I go to the very end, there's nothing else to remove. Right? So the Sieve of Eratosthenes, which of course is an ancient thing, it comes from the ancient Greeks. It's a way of producing a list of all the primes, which is actually much more efficient than the naive way, which would be sort of first you take the number 2 and you're saying, is that a prime? Well, is it a prime? You will see if there's something that divides it. There isn't, so 2 is a prime. Right? Then you try 3, then you try 4, then you try 5, and so on. And this is something that would take a lot more time than what we just did. Right? So in a sense, and this is a theme of what we're doing in week number 6, and indeed a very important idea in computer science, which is quite often useful in experimental mathematics, is that I'm somehow using that I had a list of all the numbers and started crossing off things, and the fact that I had this list is extremely important for making an efficient algorithm. So in a sense, I'm trading space for time, because I'm using the fact that I have this list, which is essentially something in the memory of my computer, that I can make my program run more efficiently. So this is one of the things, of the many things that we're going to discuss in this course, that has to do with writing efficient algorithms.